We're going to break down everything you need to know so you can walk into your exam feeling totally confident.
So here's our game plan. We'll start with the why, the language of chemistry. Then we're going to roll up our sleeves and get hands-on with writing and balancing equations. After that, we'll decode what they're really telling us, and finally put it all into practice to solve the kind of complex problems you're definitely going to see on your exam.
Okay, so let's dive right in. Why do we even need chemical equations? I mean, can't we just use words? To really get why they're so powerful, let's first imagine a world without them.
On one side, look at this. Describing a reaction in words can be this long, tangled mess. It's confusing, and honestly, it's pretty easy to misinterpret. But on the other side, a chemical equation cuts right through all that noise. It gives us a clean, simple, and universal way to talk about the exact same thing. That's the real power of chemical shorthand.
So, the crucial point here is that these equations are the universal language of chemistry. No matter where you are in the world, they clearly show us the reactants, that's what we start with, and the products that are formed. All right, so now that we know why we need them, let's get into the how. Let's see how we write these equations and, even more importantly, how we make sure they follow one of the most fundamental laws of nature.
This right here is the golden rule. It's the core principle of balancing, and it's all rooted in the law of conservation of mass. You can't just create or destroy matter in a reaction. What goes in must come out.
So let's get our hands dirty with a classic reaction. Zinc plus hydrochloric acid makes zinc chloride and hydrogen gas. Now, as it's written here, Zn plus HCl goes to ZnCl2 plus H2. It's not balanced. So the question is, how do we fix it? Well, if we do a quick atom count, the problem just jumps right out at us. We've got one hydrogen and one chlorine atom going in, but two of each are coming out. The scale is totally tipped. We can fix this in just a few simple steps. The key is to place a coefficient, that's the big number, right in front of the HCl. And just like that, by adding that 2, our atom count is now perfectly matched on both sides. We have a beautiful balanced equation. Zn plus 2HCl goes to ZnCl2 plus H2. Okay, so now that we have a balanced equation, what's next? Well, this is where the fun really begins. We've just unlocked a treasure trove of information. Welcome to the world of stoichiometry. It sounds like a complicated word, but honestly, think of it just like a recipe. The balanced equation tells you the exact proportions of ingredients you need and the precise amount of cake you're going to get. A single balanced equation is incredibly powerful. It gives us the exact ratio of everything involved, whether we're measuring in moles, which is just a chemist's way of counting huge numbers of particles, grams, which is their mass, or for gases, even their volume in liters. Now, when we're dealing with gases, there's a special concept you absolutely have to know for exams. It's called gram-molar volume, and it works its magic under what we call standard temperature and pressure, or just STP. And here is the magic number. 22.4 liters. At standard temperature and pressure, 1 mole of any gas, I don't care if it's oxygen, helium, whatever, it takes up this exact volume. Burn this number into your brain. It is a fantastic shortcut for solving so many problems. All right, theory's great, but let's actually put these ideas to the test. Let's tackle a typical exam problem, one taken straight from the source material. Let's imagine we're running a factory. Our goal, our big order, is to produce 1,120 kilograms of iron. The question is, how much raw aluminum do we need to start with to make that happen? Okay, first things first, let's go back to our recipe, the balanced equation. If we look at the atomic masses, we can see that 54 units of mass of aluminum will produce 112 units of mass of iron. This ratio is our key. Now we can set up a super simple proportion. If 112 grams of iron requires 54 grams of aluminum, then it follows that 1,120 kilograms of iron is going to need, well, a quick cross multiplication and voila! It's exactly 540 kilograms of aluminum. You see, the ratio stays the same no matter how big the numbers get. But, chemical reactions in the real world aren't always perfect. What happens when you don't have the exact, perfect amounts of your ingredients? That's where a really important idea comes in, the limiting reactant. It's actually super simple. Think about making cheese sandwiches. Let's say you've got 10 slices of bread, but only 3 slices of cheese. How many sandwiches can you possibly make? 3, right? It doesn't matter that you have all that extra bread. You're limited by the cheese. The cheese runs out first. And that's exactly what a limiting reagent is. It's the reactant, the ingredient, that gets completely used up first, and it stops the whole reaction in its tracks. It dictates the maximum amount of product you can ever hope to make.
So, let's tackle the textbook example. We're mixing 50 grams of calcium carbonate with 7.3 grams of HCl. The question is, which one is our cheese? Which one is going to run out first?
Let's do the math. The balanced equation tells us that to use up 100 grams of calcium carbonate, we need 73 grams of HCl. We have 50 grams, which is half, so we'd need half of 73, which is 36.5 grams of HCl. But wait a second, how much do we actually have? Only 7.3 grams. We are way short. We're going to run out of HCl long before the other stuff is used up. That makes HCl our limiting reagent. It's the one that stops the party.
Whew! We have covered a ton of ground, so let's just take a breath and do a quick recap of the key skills you now have in your chemistry toolkit.
Well, let's pull it all together. We started by seeing equations as a language. Then we learned the grammar, balancing them so they obey the laws of physics. Once they were balanced, we learned how to read them, using stoichiometry to turn those symbols into precise amounts. And finally, we handled real-world situations by finding the limiting reagent. These are the core skills that turn chemistry from confusing to predictable.
Okay, so what now? Well, the single most important thing you can do is practice. Theory is one thing, but getting your hands dirty and solving problems is what builds true mastery. So head over to the supplementary module, test your knowledge, and really solidify everything you've just learned. This is how you go from knowing it to owning it.